Thanks, Paul, for the kind introduction. Uh, this is an introductory talk, so I'm not going to go into a great deal of detail with respect to measurement equations or maybe more advanced techniques. It's also titled radio frequency power, but many of the measurement techniques span well beyond the radio frequency. I use that as a bit of shorthand. Um, any frequency from, say, 100 kilohertz on up to 100 gigahertz would be very suitable for this kind of technique, and they can be extended on up beyond a terahertz in many cases. So I have an outline. I'll tell you a little bit about how we approach power traceability and how we validate those measurements through international intercomparisons, and then give you a much more low-level introduction to radio frequency power, the kinds of things that people are interested in measuring. Give you an introduction to some of the types of power sensors that you might find on any lab's benchtop and how they work, and then talk a little bit about how NIST tries to get the best accuracy for power measurements in our labs. So I'm in NIST Boulder. It's in the United States. It has maybe 300 scientists. It's a smaller part of NIST. The main NIST site is in NIST Gaithersburg. And our mission is really to enhance economic security and improve quality of life. And we do that by developing measurement standards and technology. And you might ask how developing technology and standards improves the economy. Well, every microwave component, or almost every microwave component, has a data sheet, and there's almost always some specification related to microwave power. It might be how accurate a power measurement is, or how much power something can put out, or what the damage level is for some power measurement. So it's critical that if one company has a data sheet and they want to sell an instrument and another company or a person wants to buy it, then they need to be able to trust that when they buy something from one company, the things that are in its data sheet are going to agree with measurements made with an instrument from another country in another part of the world. And when they do measurements, they'll get comparable results. So this has been a problem for many, many thousands of years. It's probably as old as trade itself. So this is an example of a length standard that's more than 4,000 years old. So by establishing standards for things like microwave power, we can facilitate trade and drive economic growth. So I see many of the names in the audience are folks in the metrology field. So I have the official definition of traceability from the International Vocabulary of Metrology, the VIM, and I'll read it. It's the property of a measurement result. We have to measure something that can be related to a reference. You have to have something else that you've measured and characterized, and something maybe that's well known, through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. So this brings up some questions. What do we measure? And what references do we relate it to? So at NIST, one example of a kind of power sensor that we characterize is on the left here. It's a thermistor bolometer. And on the right is the kind of instrument that we put that power sensor in to characterize it. And we don't actually characterize power. Often in the metrology field, we're characterizing some properties of the power sensor, a calibration coefficient that corrects some raw power measurements made with the power sensor and makes them more accurate. And we're trying to get the calibration constants that correct the power measurements. So that's the thing we're measuring. Here's another example of a kind of power sensor. This one's a rectangular waveguide power sensor. So there's some DC connections that you make at the top to put DC power in. And there's a little rectangular aperture at the bottom where RF power goes in. This one operates from 50 to 75 gigahertz. And you can see the corresponding microcalorimeter on the right where we characterize this kind of power sensor. So for every type of connector, we build one of these microcalorimeters. So they're pretty specialized instruments. They're usually home built at National Metrology Institutes, and they really work with a specific type of power sensor. So what do we ultimately compare to? We ultimately compare to some fundamental constants. So the idea is that everybody in the world and maybe the universe has access to the same physics. So if we do a measurement that depends on a fundamental constant, and then we do another measurement that depends on that, and we keep track of our uncertainties at each step, then anybody who does measurements should get comparable results as long as they keep track of their measurement uncertainties. So that's a very nice story about how to make measurements done in different places by different people with different equipment agree. But it's nice to also validate that that works. So in addition to doing measurements that tie to the fundamental constants of nature, we also send devices around the world and have different laboratories characterize them and check to see that everybody's measurements agree, so that if a company gets a calibration in one country that traces to measurements done at a primary lab, then they still agree with some other company's measurements that got traced to another country's primary lab. So the most recent international intercomparison among metrology institutes was completed in 2020, and it focused on a power sensor that operated in the WR15 band, 50 to 75 gigahertz. This is the routes that the sensor made around the world. So there was a bunch of different national metrology institutes that characterized the same device. And they characterized a couple of different properties of the sensor, some calibration constants. We'll get into what those mean a little later. One of them is the effective efficiency of the power sensor, and another one is the calibration factor. So on the top graph, there's effective efficiency measurements of one of these power sensors at a particular frequency made in a bunch of different countries around the world. And you can see the red line, the bold red line, is the average of those measurements. And the individual countries' measurements are plotted near that. And to within their measurement uncertainties, they all agree quite nicely. It's a very nice story. Okay, so that's sort of a high-level introduction to how our measurements are tied to the fundamental constants that underlie the SI base units, and how we validate that measurements are accurate to within the uncertainties of the measurement and compare them among different people around the world. So what do we actually mean by RF power? Well, it has power in it, so that's energy per time. If you're driving some frequency domain waveform, some sine wave, into a resistor, for example, then there's some current and there's some voltage through the resistor at some time, and there's some instantaneous power that's being dissipated. That's the blue curve. It's going up and down quite quickly at the carrier frequency of the sine wave. And in general, there are instruments that can measure the instantaneous power, the instantaneous voltage, but they're quite cumbersome and quite bulky and really overkill for most applications. Quite often what we want is the average power. So not the instantaneous power, but if you average over all the peaks and valleys of the carrier frequency, what average power do you get? So power sensors that you might find on a benchtop, rather than in a National Metrology Institute, typically measure something like an average power. Though not every waveform is a sine wave. So in a radar signal, you might have pulses with chirp frequencies. In a telecom signal, you might have amplitude or phase or some combination of modulation schemes. And the waveform isn't just a CW signal that has some average power. So you might want to know something like the peak power for an intermittent pulse that's going out. Or you might want to know, if you're designing an amplifier, you might want to know what the highest peak power is compared to the average power, so that you can trade off the energy efficiency and the linearity of the amplifier and design an ideal amplifier that carries the signal that you want to transmit. So often you need time resolution. And so we talk about another kind of bandwidth of the power sensor, which isn't the carrier frequency, but how quickly it can do measurements in time. So this is often called the video bandwidth of a power sensor. Another important factor there is linearity. So if the power sensor doesn't measure the peak power quite as accurately as a low-level power, and it tries to average those together, it's not going to get a very accurate result. So the linearity of a power sensor, in addition to its sensitivity and time resolution, is another important factor. There's another factor that's pretty important. It's the reflection coefficient of a power sensor. So if you have some source over here and a transmission line, which in this case is very idealized and simplified, and it sends some power into a power sensor, some of the power sensor gets reflected off of the power sensor, and it might go back to the source, and then some of it might get reflected off of imperfections in the connector or the transmission line or the source and come back to the sensor, and that can happen a bunch of times. So the incident power that the sensor sees might include some multiple reflections. If you want to avoid that, you should make your sensor well matched, and that prevents some reflections and really minimizes the error that comes from a superposition of the power incident on a reflectionless match and the power that the sensor actually measures. So ideally, you want to have a well-matched sensor, and then you don't have a large amount of mismatch correction to deal with. Even for a well-matched sensor, if you ignore the mismatch corrections and just connect your signal generator to your power sensor and read out the power sensor without thinking about the reflection coefficient of the sensor and the reflection coefficient of the source, the dominant source of uncertainty is going to be most likely the mismatch corrections. If you do carefully consider the mismatch corrections, and some of the most advanced power sensors let you just put in some numbers for reflection coefficients and they'll do the calculations for you, which is quite convenient. If you do those corrections, then the dominant source of uncertainty is usually the calibration of the power sensor. So how accurately the constants were set that correct the raw power measurements to what the power sensor actually tells you. There's two different forms of calibration constant that are pretty common. The most popular one by far is the calibration factor, the one on the right. And that one tells you how much power is really incident on the sensor compared to the amount of power that it read out. So that includes the reflected power from the sensor generally, and it also includes another correction factor, which is called the effective efficiency. And that one tells you more about, compared to the amount of power that actually got absorbed by the power sensor and not reflected, what did the power read? So usually this one is less than 1. The sensor doesn't see all the power that goes in. And this one is even smaller because it includes some reflection. So now I can dive into a couple of the technologies that underlie the kinds of power sensors that you might find on a benchtop. A very common type of power sensor is a diode power sensor. These are very fast sensors and very sensitive sensors. And the idea here is that if you put in a sine wave into a nonlinear device like a diode that only allows current for the most part to flow in one direction, it's going to rectify the sine wave, and you get some DC component that tells you about the amplitude of the sine wave. So if you zoom in on the IV curve of a diode, then in the small signal regime, the output at DC from the diode is proportional to the input RF power. There's just one frequency. And in a large signal regime, it's proportional to the square root of the power. So as you go up in power, you have at low powers a nice linear regime, and at high powers a sublinear regime with respect to power. So it's a nonlinear device, but it does measurements that take high frequency power and convert them to DC signals. It's all in the electrical domain, and electronics are pretty fast. So on the whole, it's a pretty fast power sensor and a pretty sensitive power sensor. So this is a very simplified schematic. All the circuit schematics will be greatly simplified because this is an introductory talk. If there's some source, then the power sensor might have a diode in it, but diodes are also sensitive to temperature. So you can buy a diode thermometer if you want to. So it's not ideal to use the diode itself as the termination for the RF power, even though that would give you the most sensitivity. It would also make the reflection coefficient sensitive to temperature. And we want to have a well-known and well-controlled reflection coefficient to avoid mismatch uncertainty. So you put a different resistor in there that's stable over temperature, and your power sensor will be well matched. And you get some of the RF power to go across a diode or two or a number of diode paths, and then you get a voltage output. So some of the trade-offs for a diode power sensor: they have excellent sensitivity, they have pretty fast responses, so they can measure a peak power or an envelope as a function of time. They're generally quite well matched and have an excellent dynamic range. A couple of the downsides are that they're generally not as linear as some other types of power sensors that I'll talk about. And since they're not as linear, they require a little bit more correction, and so they're not as accurate as some other types of power sensors in general. I put some numbers up here to give you a sense of the kinds of levels and speeds of signals that you can measure, rough orders of magnitude so that you can get a sense of the landscape. You know, if you buy a particular power sensor, it might be a little bit more or less sensitive or have a different video bandwidth. So some of the key applications are low power measurements, time resolved measurements, and peak power measurements. Getting towards a little bit more accurate, and I'm going to build towards more and more accurate power sensors. Another type of technology you might encounter in power sensors is a thermocouple. So if you have something hot and something cold, and you put two different conducting materials between them in a special configuration, red and blue wires are different materials in this diagram, then you can get a voltage that's proportional to the temperature difference between two things. And we can use that to make a power sensor. The way you do that is to take a source power and terminate it with a load that converts the power into heat. And that heats up some thermally isolated object. Sometimes there's a microfabricated membrane that thermally isolates a sensor element from the thermal environment around it. And that something on that island gets hot, and you put a bunch of thermocouples from the island to something at ambient temperature, and that gives you a voltage that tells you how hot the thing got, and by doing so, roughly how much power was incident on it. You can go through from first principles and try to estimate the coefficient for how much voltage you get for power. But if you do that, you typically end up with more uncertainty than you would get by putting a known power in and just coming up with a scale factor for the output voltage. So these guys usually get calibrated with a different system, ultimately. It's a great all-around power sensor technology. Since it does convert an electrical signal into a thermal domain and then back to an electrical signal, it's not generally as sensitive as something that stays in the electronic domain. So it's not as sensitive as a diode power sensor, for example. Since it involves heating something up and cooling it back off, the measurement speed is not as high. So you might get 100 measurements per second, a slower envelope measurement capability, but it's generally more accurate and more linear than, say, a diode power sensor. So it's very popular for average power measurements, but not so much peak power measurements or waveform measurements. And it's very popular for calibrating the source levels for signal generators and things like network analyzers, because those are often putting out a narrow band or single frequency signal. Another technology which is much more popular at National Metrology Institutes and maybe less common in applied laboratories is a bolometer. So a bolometer is a temperature-dependent resistor, and you can put DC power into it and it gets hot and changes resistance, or you can dissipate RF or microwave or terahertz power in it and it'll get warmed up and change resistance. When we measure a reflection coefficient, we like the resistance of the resistor to be the same all the time. So these are typically operated in a feedback loop where you put DC power in with a meter, and the meter tries to hold the resistance constant by changing the amount of power that's going into the resistor. And it can also measure that DC power. There's a current and a voltage. So when you add some RF or microwave power to the resistor, it gets warmed up, and the DC power meter will back off the amount of DC power that it's putting in to hold the resistance constant. And by looking at the change in DC power, we can get an estimate of the RF power that's going into the device. Since there's power from two different sources going into the same resistor, we have to have some filter structure so that the DC power doesn't go back into the source. So these power sensors typically don't operate down to DC. There's some low frequency cutoff where they'll work. So in general, they're not as good as what you might like for sensitivity and dynamic range and time resolution as some of the other kinds of power sensors we've discussed. But from a metrology perspective, they have this wonderful attribute that they're very linear. So the DC power measurements tie to voltmeters and current meters or resistance meters, and DC measurements of resistance and voltage have more decimals of accuracy and precision than I dream of in microwave measurements. So it's very nice that this kind of power sensor inherits the linearity of DC metering electronics. That can make it very nice as a metrology tool for microwave connections. So this is a common transfer standard for calibration laboratories and instrument calibrations. And if you want the highest accuracy measurements, this is the kind of power sensor that you might be interested in. So one thing all of these kinds of power sensors have in common is that they're typically in a metal package. So even if you had a perfect power sensor located at some reference plane inside of a device, you'd have metal that connected that power sensor to a coaxial or waveguide connector, and that metal has losses associated with it. It generally has to be there because the connector needs to be a single moded waveguide so that you can do a scattering parameter calibration. And this is sort of an unavoidable source of inaccuracy in packaged power sensors. But we can think of this not as a bug, but as a feature. So if we just think about the absorbed power as a function of time, the DC metering electronics in a bolometer are going to try to heat up the resistor, even when there's no RF power, and hold it at a constant resistance. Then if we add some RF power, the DC metering electronics are going to back off the DC power. And by looking at the change in DC power, we can get something proportional to the RF power, but it's not a perfect measurement. There's always extra loss. Typically, it's less than the amount of RF power. So there's some extra absorbed power that's going to heat the whole body of the power sensor. So if we think about the entire power sensor and how warm it gets when RF and DC power go into it, then maybe we can measure the total amount of power that way. And that's the idea behind the primary power measurements that are done at many national labs around the world. So the idea is that the whole power sensor gets treated as a thermally isolated body, and we try to build a special instrument that separates it from the environment. And then we put some RF power into it and some DC power into it, and we see how warm the entire power sensor gets. And that temperature rise is proportional to the DC power and the RF power that's going into it. And of course, there's yet another correction factor because no measurement system is perfect. But the correction factor for a microcalorimeter is typically more stable than the corrections for a power sensor. And typically it's a smaller correction. And typically there's people working very hard to estimate that correction. So this kind of approach is how we ultimately tie RF power to the SI. There's DC power measurements that have a current and a voltage associated with them, or a voltage squared and a resistance in some cases. And it's those low frequency measurements that get tied back to the fundamental constants. And then we do some scattering parameter measurements, which are also traceable to fundamental constants, to tie the RF power to fundamental units. So this is an example of a picture of a microcalorimeter. Those rectangular waveguide WR15 power sensors are in here. And this bit, while it looks like metal, is actually gold-plated plastic, and it thermally isolates that power sensor from the environment. So I'll overlay a bit of a schematic on top of this. Some DC power goes into the top of a power sensor, some RF power goes into the bottom, and right in the middle here, there's a commercially purchased thermopile that gives us a signal that's proportional to temperature. We don't actually need to know the absolute temperature, it turns out. We just need something proportional to temperature, because we're going to calibrate the constant of proportionality with DC power anyway. I should note there's probably some metrologists in the audience that say this isn't a calorimeter at all, nor is it micro in the sense that it's small. Micro here is an abbreviation for microwave, and calorimeter is just an inaccurate name that we retain for historical purposes. This really is a watt meter or a power meter and not a calorimeter. It's measuring power and not energy. But we retain the name for historical purposes. It's been called a microcalorimeter for longer than I've been around, so we're going to keep calling it that. So for something like a milliwatt or 10 milliwatts of power, the whole body of the power sensor doesn't actually get that warm. It might go up by about 1 degree C. So getting rid of environmental temperature variations is pretty important. One way we try to do that is by building a thermally symmetric circuit so that if ambient temperature changes, both of these power sensors that are in this meter are going to get warmer and cooler to the same degree as the environment gets warmer and cooler. And we only measure the temperature difference between them, or something proportional to the temperature difference between them. And that gets rid of some ambient temperature variation through common mode rejection. That's why there's 2 power sensors in here instead of just 1. In addition, we try to put these in a very quiet thermal environment. So they're typically submerged in a bath of water that's controlled down to about 1 millikelvin to try to improve our signal to noise measurements for those temperature differences. So if I think about this in the same kind of trade space as those other benchtop power sensors, there's many downsides. The dynamic range is quite limited. The signal to noise just isn't that big because the whole power sensor doesn't get that hot compared to a tiny element inside it that's sensing power and maybe gets quite a bit warmer. They have kind of limited sensitivity, but maybe the biggest trouble with them is that they're very, very slow. So you have to wait for the entire power sensor to come to thermal equilibrium at each frequency, which might take an hour per frequency. Maybe you want to do 500 frequencies for a given power sensor. So you're looking at weeks of measurement time just to characterize a single power sensor, which doesn't make it the greatest applied power sensor in the world, but it does offer the best accuracy and also excellent linearity. So this is the kind of power sensor that's typically operated at National Metrology Institutes. It seemed to change the slide. Oh, there we are. So I've talked a little bit about the primary RF power experiment. It is a measurement that's done in a microcalorimeter and characterizes the effective efficiency of a power sensor. Once we know the calibration factor and effective efficiency of a power sensor, then we do a secondary measurement where we can transfer the power measurements with our calibrated power sensor to a source, and then we have a calibrated source power, and then we can put any power sensor that we'd like on the test port and put some known power into it, see what power it reads out, and come up with a correction factor for any off-the-shelf power sensor. So NIST offers 2 different kinds of measurement services. One is for the kind of specialized sensor that goes in the calorimeter, and that offers the lowest possible uncertainties. And the other is a direct comparison measurement that transfers microcalorimeter calibrations to any off-the-shelf power sensor. So with that, I'll summarize. RF power measurements are traced to the fundamental constants that are defined in the SI system of units. Measurements of power sensors get validated by comparing results from metrology labs around the world. There's a number of different power sensors. I talked about 3 of them. There are many, many types of power sensors that are commercially available and at the lab scale for very low power and very high power and different kinds of measurements. In general, they make trade-offs in sensitivity and linearity and dynamic range and measurement speed, among other specifications. And I hope that I've shown you a little bit about how we do primary measurements and how we get the lowest uncertainty by putting power sensors in a microcalorimeter. And with that, I thank you all for your attention.